everything we always wanted to know about scenario generation and sampling methods. So I will let Güzin then start your class. Thank you.
Well, thank you for the invitation. I have the microphone on. Everyone can hear me well. Great. So my slides are in the red. My school is Ohio State University, which is red and gray. So I've been accumulating a lot more red stuff. Actually, there's also this Hello? Ah. Okay, I think it's better. All right, so this is just a regular sample mean. You can think of it, like it's just a statistical estimator of that. But when we optimize it, obviously the statistical properties will change. So you've seen a lot of these. Tito talked about them, including some simple things versus some more complicated things like large deviations theory. Of what's happening to these. So again, let's recall the notation. I have X star, right, which is an optimal solution to the true problem. These are all true problem sort of parameters. The set of optimal solutions, and then nu star is the optimal value. And then when I solve the sample average approximation, these are my notation for an optimal solution of the sample average approximation with sample size n. Similarly, set of optimal solutions and the optimal value of the sample average approximation, right? So I'm using these to actually statistically estimate these guys, all right? So what have we seen so far is the standard Monte Carlo, which is I take independent and identically distributed IID samples. They have the same distribution as my underlying XC, okay? Whatever it is, I assume I can sample from it. Sometimes just coming up with the sample can be actually very difficult, right? But let's assume we can sample it, we generate these IID samples, and we look at certain properties. So one of the more general ones, so for example, if I go back, right? If I do IID sample of this, the G function will carry it out. So this is an unbiased estimator of the expectation. Right? It has strong law of large numbers, central limit theorem, etc. But when I optimize the sample mean, the properties change. So it's no longer unbiased. Optimization creates a bias, right? So that's one thing you have seen so far. But we still can have consistency under certain conditions, right? Not always. You must have some properties on the set of constraints, on G, and so on and so forth. Also, under even more restrictive conditions, you can get some kind of a central limit theorem. So in this case, this assumes a unique optimal solution. Right? Again, this is a recap of what Tito have already covered. If not, this is not going to converge to a normal distribution if there are multiple optimal solutions, but something more conservative, minimum of a negative, a minimum of a bunch of normals. And then there are obviously large deviations, exponential rates of convergence, and so on and so forth, right? So optimization will change the sample mean properties. yet we can recover some of them under some more restrictive conditions. All right. So why do we want variance reduction? Right? The session is going to be about different sampling techniques and different ways of making our estimators better, right? So why do we want variance reduction? Very simple answer, because we want better estimators, okay, shortly put. But if I want to go a little bit longer into that, so again, this is just the objective function value evaluated at one particular decision vector x, right? This expectation. And I cannot usually calculate it. It's typical problems will have very easily 40, 100, 200 dimension of this xi, right? It's going to either think about it as a continuous distribution multidimensional integral, good luck, and then G is already very complicated, right? It could be a multi-stage problem where it might have nested optimization problem. Just to evaluate that function can be very difficult. All right, so I'm going to estimate it by the sample mean approximation, or right? So let's just, for illustration purposes, I estimate this sample mean, but then I also provide a confidence interval on it by giving plus or minus 2 standard deviations, all right? Because point estimation only gives you some information. It doesn't give you all the information, right? So a better way of thinking about estimation is interval estimation, so that also gives you variability around your estimates. So plus or 2, standard deviations of my estimator. And a very simple example here, I have 2 estimators. They both tell me with the same sample size, they estimate that the objective function value at x is going to be 10, okay? But I have my variance, and that's going to be the first one estimator, let's say, have variance, or I estimate that as well, so 25, versus the second one is 0.25. So if I look at a confidence interval, plus or minus 2 standard deviations, so 5, it's 10, so plus or minus 10, it says, hey, point estimator is 10 objective function value, but it's in between 0 and 20. Versus, if I have a much smaller variance, I do the same calculation, it's just 1 plus or minus 1, so I say, hey, it's 10, but it's in between 9 and 11. Which one do you prefer? Obviously, the second one is significantly better estimator, right? So this is a very common issue in statistics, simulation. We want to reduce the variance, obviously, because we get much better estimators, all right? So let's just take a look at standard Monte Carlo. I'm sure you have seen this in Tito's slides as well, right? So if I take a regular IID sample, and that's my sample mean, variance of that, these are independent identically distributed, n squared goes out, I have times n of those. So it's variance of one of these terms divided by n, right? So to decrease the variance, I can always increase n, all right? And I can increase n, and just like, so if I want to actually go from a half-width, confidence half-width of 10 by order of magnitude less to 1, right? So by 10 times reduction, I need to decrease the variance by 100, right? So there's a square thing because of the standard deviation, and 1 over n for the variance, right? So we can increase the sample size, but to gain a little bit, we're going to pay up a lot. All right? And especially when we're dealing with optimization. Even if we don't deal with optimization just like we're doing here. So far there's no optimization, right? I'm just trying to estimate it for a given x. I'm still not doing any optimization so far. So even with that, I don't want to increase the sample size n, right? Oh, just a side note, by the way, this variance is typically not known, but you can estimate it just like a regular standard variance, and that's what you do in classical statistics, right, to form confidence intervals and whatnot, or approximate confidence intervals. So I don't want to increase the sample size, definitely, even when I'm not optimizing, because as I told you, this G function can be very, very complicated. A bunch of multi-stage, nested optimization problems, for example. On top of that, when I also optimize, right, depending on the problem type, if I increase the sample size, the computational burden is even going to increase more. So it's not a desirable thing. What I want to do is I want to decrease the variance without increasing the sample size at all. Okay? It's a really well-studied topic in statistics and simulation. Not so much, I mean less so, I should say, when we have optimization of sort of these sample means. All right? So when you use this Monte Carlo simulation and use it for optimization of stochastic systems, right? Less studied, and it actually can be a lot more important. Why? Because most of these Monte Carlo simulation-based methods, they generate iteratively estimates of this type. They also generate cutting, gradients to optimize, to go in the, best direction and whatnot. So if you have really poor estimates of these things, your algorithm is going to continue forever. It's not going to stop. Convergence is going to suffer. You're going to make incorrect decisions to stop, and so on and so forth, right? It's actually a lot more important when you're in the optimization setting. Okay? But when you're in the optimization setting, obviously the analysis can be very difficult because you also have an operator, an optimization operator in there. All right. So far so good. Very basic introduction. So by the way, I mean, I believe some of you already know these topics. So if you know them, I don't know if you've ever seen any of these variance reduction techniques. All right, so this is all like an introductory level. If you have, might be a little bit boring, but I just want to show sort of more the basic ideas and commonly used variance reduction techniques, and then see what happens when we use it in optimization. All right, so that's the aim. All right, some of the variance reduction techniques we're going to cover today. Antithetic Variates, one of the simplest ones. Latin hypercube sampling, quite simple but also effective. Quasi-Monte Carlo can get very complicated. There's a lot of people working on that, and then you want to randomize it to get sort of more sample stuff. Importance sampling can be important in some situations. And things like control variates, right? So these are used a lot in, as I said, statistics and simulation communities. And we're going to see what happens when we do optimization. All right. So, and the way I'm going to do it is like this. So first, it's easier to do this. I'm going to introduce these techniques in the context of estimating, there's an expectation here. So it's a small g of x, right? I want to estimate the expected value of this for a given x, so without any optimization. So just like regular statistics. I want to estimate a mean, all right? So I'm going to introduce these techniques for that, and then at some point, toward the end, every time I introduce a topic, there's a bit of a literature slide or two that says, so-and-so used it in this context, it behaves like this, kind of like pointers for you, what happens in stochastic optimization. And once we go through these techniques, then I'm going to basically talk about what happens to the properties, all the properties you have talked about when you do SAA, right, this bias, large deviations, exponential rates of convergence. What happens if we use these variance reduction techniques? So we're going to discuss them in a little bit more detail. So that's how it's going to go. Okay? Before we start, so some common themes. If you're actually new to this topic, right, and if you want to create your own variance reduction, there are several things that happen a lot. So if you can induce some kind of correlation between your random, the thing you're trying to estimate, and maybe something else that's easier, if you can exploit it, you're going to get variance reduction. Okay, so correlations actually can be good for variance reduction. It might also depend on the type of correlation, negative or positive. Sometimes negative is good, positive is bad. Sometimes either type of correlation is good, depending on the technique. All right. Another way to reduce variance is sampling more uniformly than a random. Just if I throw darts on the board, right, or the screen, versus if I arrange it in such a way that it's like more uniformly covers this area, I might do a better job, right, because I represent my uncertainty significantly better. So that's, again, a very intuitive and a common theme among variance reduction. Some of them actually do both, okay? And then, especially when you're dealing with risk measures and some kind of like tail probabilities, rare events, you might want to change the sampling so that you sample the important parts a lot more. So I believe Tito must have given one example where he's trying to solve like a routing type of problem, and there's a chance constraint in there. It's really rare probability, or depending on how you look, either a very large probability, or you write it the other way, very, very small probability chance constraint. If you do sampling, I mean, regular Monte Carlo sampling is kind of hopeless there, right? So if you're under those situations, you might want to do something else. Okay, but so these are common themes we're going to see throughout this. All right, so let me start with something called Antithetic Variates. I assume you've never heard of this before, okay? All right, so the idea, well, hey, we're going to use negatively correlated random variables, so we're going to exploit the correlations, okay? In this case, we want negative correlation, and it's going to become clear in just a minute or two. So antithetic variates, they come in pairs. So my sample size, I'm going to assume, is even. Oh, another thing, most of this talk, I'm going to assume the components of Xi are independent. So I have a random vector, Xi1, Xi2, Xi3, however many, like dimension d Xi, let's say. So these I'm going to assume are independent. So most of this talk is like that. If they're not independent, there are ways to deal with them, okay? So there are techniques developed, for instance, for antithetic variates to deal with them. But another way of doing it is, for example, you know, I might have different demands, let's say n demands, but then I want to write, these are correlated, okay? So these are not independent. But I might create, let's say, you know, some kind of like a regression. Think about it like a regression, right? So I might actually map it to something like this. I'm just making it up, by the way, right now. Okay? So, all right? So these guys, I can have them independent, but the DIs, they depend on the same things with some coefficients, let's say regression coefficients, then these will be dependent, all right? If you can create this kind of a structure, then you go back, work with these instead of say your problem has a bunch of demands, you need to meet the demands that are correlated, but go ahead and maybe create something that's underlying some independent components there, okay? So this could be, I don't know, the economic factor, how the economy is doing. I don't know, this could be some kind of raw material, like maybe depends on climate, for example, right, how the weather is. So if you have that, you have the material in a different way, or some demand, say water demand might depend on, right, climate, for example. So you can have those independent components. Just to let you know, you can do more general than this, so that was a side comment, but pretty much that's what we're going to assume throughout the talk again. All right. So antithetic variates, back to that. So these are uniforms. All right. I'm going to sample actually n over 2 from a uniform of d Xi. Right. So if I have 2, it's a unit cube. Once I sample these observations, and these are, by the way, independently and identically distributed, obviously, observations, then I'm going to create the antithetic pair. So I take the first observation, and I do 1 minus that. So component-wise, each component, I'm going to do 1 minus. All right? And then that's going to be my sort of first antithetic pair. So U1 will go with the opposite end. So you know, the last one will go 1 minus that. That's the pair. All right? Then, assuming my cumulative distribution function of Xi is invertible, right? In most of cases, it will be. Or if it's discrete, you can also take, usual inverse cumulative distribution function. Then you invert the uniforms into your X's. But these are going to be in pairs. All right? So this is the first antithetic pair, second antithetic pair, and the last antithetic pair. Total, I have n observations. So, by the way, U1 is a uniform. 1 minus U1. Is it still a uniform? Absolutely. Are they independent? Obviously not. You know, one is 1 minus the other. So there's a very strong relationship there, right? Actually, it's very negatively correlated. If one is high, the other one is low. If one is low, the other one is high. And that's what we want. But we also use and map it into the x's. Okay? So. I'm sorry?
Could you use other families of
Oh, absolutely. Oh, you mean here?
for example, for you?
Yeah, but that's usually taken care of at the, whatever your distribution here is. There might be some issues, so some of them not invertible, perhaps. It sometimes, depends on what you mean by not invertible. So like, it might be numerically invertible, like the normal distribution, right? So you can get a numerical answer, maybe not analytically. But for the most part, this works, okay? And this is a very common way of doing it, right? So, and the reason is cumulative distribution function is always between 0 and 1. Throw a dart in there, you just pick the value that gives you that CDF. So, all right, so just a little, showing how this works. Obviously, if my, so this is uniform and I mapped it into this kind of a, say, normal or something like that, right? So C1 here, then its antithetic pair will be on the opposite end, 1 minus that. C2 here, then its antithetic pair will be there. So it's as simple as that. So very simple, and it can be effective, moderately effective at least, right? So if I look at the AV, antithetic variates estimator, then I'm gonna do a little bit of a change. So before I had all of these GXCs, I summed them up across n samples divided by 1 over n. Now, every time I have a pair, I sum them up and divide by 2, okay? And I have n over 2 pairs, and that's my antithetic variates estimator, okay? Now, it's an unbiased estimator, all right? And it's easy to see. I mean, this is, on one side, on the other side, I take, you can also see it from here intuitively, right? If I'm trying to estimate the mean, I take this and that and this and that. It's actually going to give me something better for the mean when I do these two, divide them by 2, and all of that, right? So you can see intuitively why it would reduce the variance, because I'm actually concentrating it on the mean a lot more, all right? So, and it has this variance. So this is also very easy to derive. Everyone can see what's happening here, right? It's pretty easy. So you can think of like just 2 of them, right? I can just take 2 of these things. So if I have IID sample, the variance, or n is 2. So if I have IID sample, I have the variance of this, variance of that. They're independent, identically distributed. So I have 2 of the variance, and 1 over 2 goes at 1/2. Times 2, it's going to be 1 over 2 variance. So this is the variance of the standard Monte Carlo. On the other hand, for the antithetic variates, I no longer have independence, so I need to look at the covariance terms, okay? So in addition to that, I will have covariance added to my variability. And hey, if the covariance is less than 0, I have reduced the variance. I'm done. Okay? So I want negative correlation. It's very simple, so if you want to implement it, go ahead. It's one of the easiest things. So when will we, by the way, so the question becomes, when will we induce this negative correlation? So when we have the uniform and 1 minus uniform, I already have negative correlation. But in general, it's going to be depending on, once I do the transformation from U prime to Xi prime, right? I might lose a little bit of negative correlation. Usually the cumulative distribution function, that's monotone and stuff like that, so it's okay. But this function can actually mess it up. So there's the G, right? The G can map it in completely different ways and basically make me lose my negative correlation. So we have to be careful about that. So one thing we do know, so if this G, is bounded and it's not constant, so if it maps to a constant, it's all constant anyway. But the most important thing is if I have monotonicity in each component of Xi, all right, then I'm going to preserve the negative correlation. Right? So monotonicity, when you induce correlations, becomes important. So you can see this in variance reduction techniques quite often popping up. So what does it mean, by the way, to be monotone in each component of Xi? I fix one component of Xi, all the other components of Xi, and I look at one of them. If I increase it, if my function is monotonically increasing or decreasing, either way, right? According to that one component, all the others are fixed, then it's going to be monotone in that component. If I do it for all the other ones and have monotonicity, then I'm good to go, right? So the big question is, when do we have monotonicity and when we don't have the monotonicity, right? For example, again, you have seen this in, I'm pretty sure, in Tito's slides, right? The two-stage stochastic linear program. So maybe the first stage like allocates some capacities to some plants and decides on some decisions to do strategically, and then say demand is unknown and some operating costs are unknown, but once you know them, you can actually operate your system and minimize your sort of, say, capacity allocation costs plus your expected operating costs, okay? Something like that. So now, it's linear here, and these are linear things. And I have such, I wrote it in a little bit different probably than Tito, but let's see. Okay, what do I have here? Okay. So for example, recourse matrix is this matrix that shows up here in the second stage. This should be fixed. When it's not fixed, if it's random, it's almost very difficult to determine what's going to happen. If something is increased and decreased, it messes up things. So fixed recourse always helps. On the other hand, another thing is, okay, I can tell it. So this should be non-negative, and another important thing is you should have inequality constraints on the parts where you have randomness, okay? And why? Because think about it like this. So I need to meet my demand, right? So let's say this constraint says meet the demand, but the demand is random, all right? So if I increase my demand, what's going to happen? I need to meet the demand. What do you think my cost is going to be? How is it going to be affected? So I need to meet the demand. To meet the demand, I need to produce more. I need to ship things more, etc. What do you think will happen to my costs? They're going to go up, right? So if my demand goes up, then my cost possibly will go up. Or I can have another side, like a less than or equal to constraint. Then I have a resource. I have to remain within that resource. Suppose a budget. There's a lot of budget uncertainty, right? Or time something. So you can also say less than or equal to some available time, say 24 hours in a day, but I want 40 hours in a day, only for myself, right? But if I had 40 hours in a day, if I increase this, then maybe, I can produce more, something like that, right? So this inequality will give you this monotonicity. If you have equality, things can go either way. You cannot say anything, all right? Most of the time. So some problems, even though they're written by equality, you can equivalently write them as inequality, all right? Like the demand constraints, meet the demand constraints. Then you can have monotonicity. But there are some other cases you cannot guarantee. So that's an important factor, and this being fixed, and you need non-negativity so that things go in the right direction. So this is one way of looking at monotonicity. And under those conditions, it would work. But be careful, it can also backfire. This very simple method, if you don't use it, when you lose monotonicity, by the way, I lost my slides, so some of them didn't compile well, and so on and so forth. So if monotonicity, this is Koivu, by the way, if monotonicity is lost, it can actually increase the variance up to like doubling the variance, right? And you can see that simply from this term, right? If this is my standard Monte Carlo, somehow I induce positive correlation instead of negative, I'm going to increase the variance. It's worse than what I started with, okay? Very simple, but need to be a little bit careful. This is, again, all no optimization. So when we use it for optimization, this is a Framer-Linderoth paper. Again, apologies for these question marks that will pop up here and there. So on a news vendor problem, right, you can show that analytically it will always decrease the bias, by the way. We're trying to reduce variance, but this is a really nice side effect, okay? And by the way, this side effect is observed for other variance reduction techniques. When I do variance reduction, I actually get the benefit of reducing my bias as well, all right? And there's a reason for that, and we'll discuss it a little bit more. But it can also increase and decrease the variance depending on the parameter, same thing. So you don't know sometimes what's going to happen. When it's effective, people have used it with other variance reduction techniques to make them better. And for when we have monotonicity, it usually achieves modest variance and bias reduction, actually, all right, for some problems. So just to let you know. Latin hypercube sampling, next. One of the most commonly used things. All right, so now the idea is to use stratified sampling in a less computationally intensive way. Again, it's going to induce some correlations, by the way. Then it's going to also fill in the space a little bit differently than random sampling. And that's going to cause variance reduction. All right, so again, I'm going to assume components of Xi are independent. So for each component of Xi, I'm going to sample a uniform. But this uniform, so if I'm going to do a sample size of capital N, all right, each dimension, I chop it up into n regions. So the first one will be 0 to 1 over n, okay? 1 over n to 2 over n, 2 over n to 3 over n, etc. So I chop it up into n regions, and within each region on that dimension, I'm going to sample uniformly of that particular part, all right? And once I do that, so I'm going to have n of these. I'm going to have n factorial permutations. Let's have them equally likely. Then I'm going to randomly permutate them to get sort of my Latin hypercube sample. And then, again, I can use the inverse cumulative distribution to get my X's. All right? So here is an example where the dimension is 2 and the sample size is 4. So the first step, remember, on each dimension, I'm going to create 4 sample sizes. So I chop it up into 4 equal areas. So I stratify it. If it's a uniform, right, each one of these squares have the same probability. But I do the same thing here. So I generate 1 here, 1 there, da-da-da. Do the same thing on the second dimension. And so the points basically will always line up in this diagonal boxes, right? Because of the way I'm generating them. But this doesn't look very random at all. So the next step is to permutate them, right? To make them appear, fill in the space better. And once you do that, this is one example of, Latin hypercube you're going to get, okay? And if you run it some other time, even if you generate these, your scrambling might be a little different, right? Permutations. So this is how Latin hypercube works. It's, again, simple. And, one thing about stratified sampling, as the dimension increases, it can get very complicated if you want to do stratified sampling. How are you going to partition, which part, how to calculate the probabilities. I have done this for another work. You go to 40 dimension, 50 dimension, it gets more complicated. Latin hypercube is still very simple because, it tells you where to chop them up, and you're always going to create the diagonal first and then scramble and so on and so forth. So it's actually not that bad at all. So it's pretty simple to implement, and there are already codes available. So some properties. Once I do this, interestingly, not so interestingly maybe, change my mind, each one of these points is going to be unbiased, all right? Why? Because I generated them uniformly, but then I also scrambled them sort of randomly. So in the end, if I take any one of these points, they're going to be all unbiased. So I have that property. But obviously, each one of these points are not independent anymore, unlike random sampling, because I created them in a dependent way. So actually, this this correlation decreases the variance. And then if I look at my Latin hypercube estimator, all I'm doing is I generated this n samples instead of my IID Monte Carlo. I just put my Latin hypercube and take the sample average, done. And then, of course, because of the first property, then this whole thing is going to have, is going to be an unbiased estimator. Okay? Nothing, so these are nice properties. So even each one is unbiased, and of course, my sample overall is unbiased. And again, the monotonicity comes up because we have this correlation going on. If this function is monotone in each component of Xi, I can guarantee that the variance of the Latin hypercube will never be greater than, will actually reduce the variability compared to standard Monte Carlo. All right? However, again, you might not have this, but it's not like antithetic variates. It doesn't, increase it that much. There's a, more general result, thanks to Oven. So this result says, look, if I look at my variance of the Latin hypercube estimator, it's never worse than this quantity over here. This is, by the way, my standard Monte Carlo estimator. What is the variance of my standard Monte Carlo estimator? Do we remember? Just variance, not the standard deviation. Right. Yeah, exactly. Variance over n, right? So Gn of x is, just to remind ourselves, right? G of x Cj, something like that. So it's going to be variance of this individual term divided by capital N, okay? So if I plug that in here, what do I get? Variance of the individual term divided by n minus 1. And that's the variability of a Monte Carlo, standard Monte Carlo estimator with n minus 1 samples. Okay? This is the variance of the standard Monte Carlo with n samples. If you want to do a variance of Monte Carlo with n minus 1 samples, right, it's the variance of G divided by n minus 1. That's it. Okay? So what it's saying us, if I have an n sample Latin hypercube, its variance will never be greater than standard Monte Carlo with n minus 1 samples. So it can increase maybe a little bit, right? But it's n over n minus 1, so if n is sufficiently large, it doesn't actually make it that worse. So this is a nice thing. But in practice, it actually in practice, it's actually can be significantly lower. All right, can be significantly lower than that one. All right, but this is nice so that we know it doesn't make things bad. All right, so again, so here's a simple sort of a Nusswender problem. So Linderoth have analyzed this. They actually can show, so they consider a uniform demand distribution, smooth function, unique optimal solution, right? It's one-dimensional, so you chop it up into n samples. Optimal solution, optimal value will always be in one of those things. And you uniformly sample there. So when you do that, basically, you're always going to be somewhere in that region. Your bias is completely removed for this problem. So you no longer have optimization bias, which is, again, you're not doing it for bias reduction, but a really nice side benefit for this problem. So this is not general. What is general is when you do this bias variance reduction, most of the time you actually reduce your bias as well. If you know statistics, if you want to reduce bias, so you do jackknifing or some other methods, you end up increasing the variance. So there's usually a trade-off. In optimization, it looks like when you do bias, some variance reduction, you also decrease the bias. And also for the Nusswender, you decrease it considerably. There are many studies that show actually for, say, two-stage or multi-stage stochastic linear programs with recourse, it effectively reduces bias and variance, and it's easy to implement. Okay, so if you want to do this, this is one thing you can try, right? Estimating the mean. Any question? Nope? No, go ahead, go ahead. It's better that way. Not unless, like, for example, for the Nusswender problem, it's one-dimensional and so on and so forth, and the function is quite simple. You can analytically show it. But when you go to like real world problems, it's hopeless. I mean, to show it analytically, no, you know. Yeah, for some simple functions, yes, you can, but not really in general. Okay. Next up, quasi-Monte Carlo, QMC, and its cousin, randomized quasi-Monte Carlo. Okay? So here we use something called a low-discrepancy sequence to sample more uniformly. All right? These are from Lemieux. So from this point on, I believe the references are going to be correct. So this is basically, I throw a bunch of darts in that box, and then this is the random sampling. Right? As you can see, there are some empty places around here. It's completely random. But maybe that's not what I want. As I said, if I can have a more, like a nicer spread and make sure things are filled in. Like here's one example, Sobol sequence. It looks like it's got like these lines going on, but with a little bit of like shifts around it, okay? So the idea here is to do it in such a way that it's better than sort of random sampling, okay? And that's quantified by something called a discrepancy, and if it has certain properties, it's called a low-discrepancy sequence. And by the way, this is random. This, quasi-Monte Carlo, usually these sequences are not random at all. So there's a lot of like number theory, like you just generate these things as the sample size goes on. So they're actually deterministic sequences rather than random. All right. So here's another example. So these are TMS nets. It's a 032 net in base 3, for example. Many, many different ways of calculating it. So you can see here, there are like 9 boxes on each, on the big thing, on the 2 dimensions, right? And then each one of the 9 boxes have 9 boxes inside them, all right? And so a little bit like reminding us Latin hypercube. So here, for each one of these, like each row will have 1 element. Each column will have 1 element, okay? By the way, that was true of Latin hypercube sampling, okay? When I do the scrambling and all of that, each row will have only 1. Each column will have only 1 element. So here, you do it over, each one of these 9 boxes, so to speak, okay? So this is, this is one of the good ones. And there are, again, many, many different ways. I'm not going to get into details of how to do it. There's a lot of things here. Famous ones, there are some more simpler ones. There are lattice rules. So digital nets are, used a lot. Luckily, there's actually code available for them because generating them can be, a little bit difficult at times, depending on the method. So for this part, I'm going to assume, again, independent components, but also uniform distribution, each one of them, so it's a uniform over the whole dimension, okay? So I don't do the inverse, but you can do the inverse afterwards. All right. So how do I know this is a good sequence? So that's one big question. So suppose I find a way, I do these boxes, I put them in their locations and whatnot. What makes it a good or a sort of uniform? So this is something called a star discrepancy is used a lot. So there are other discrepancy measures, but star discrepancy has nice theoretical properties, so to speak. So what is it? So consider this dimension, d of xi. This is my dimension, let's say 2 or 10 or something. And I have a point set. So say my Sobol sequence will start generating these things, will start filling in my space, okay? And I can continue doing this as I increase, say, the sample size, although they're not random. And I take the first endpoints from this, and I consider hyperrectangles. So I'm on a, say, a unit cube, right? Or square, or whatever the dimension is. So I create these hyperrectangles. So give me a vector of b, all right? These v's will be obviously less than 1, greater than or equal to 0. And I generate these hyperrectangles, so 0 to v, okay? And I look at how many of my points from the sequence are in here compared to a continuous uniform distribution. Do you know Kolmogorov-Smirnov distance? some of you. Do you know Kolmogorov-Smirnov test? So it uses the Kolmogorov-Smirnov distance to do goodness of fit test. So it's actually something like that, right? So what it's doing is, it looks at, in my point set, how many that I am in this hyperbox rectangle divided by the total number of points. So you can think of it as like an empirical measure of how much I'm filling that particular space, that B of V. And then I subtract basically what will be the probability that the continuous uniform will assign there, right? So once I look at that, I need to take the supremum over all such hyper rectangles. That's going to give me the star discrepancy, okay? So it's like it's basically a Kolmogorov-Smirnov distance. So here is a, just an example. Dimension is 2. I take one of these boxes, so the first component here is 0.4, second component here is 0.7. Again, you're going to do all these boxes. They all have a corner at 0, and you're going to like consider all of them, right? And take the supremum over that. So for this particular box, my sequence has 23 points. Only 6 of them happen to fall in here, all right? So I just look at 6 over 23. That's kind of like how much my sequence filled in. And I subtract from how much, a continuous uniform will assign a probability measure over there. So this one. And that gives me the discrepancy, okay? So obviously, it's not that easy to calculate for general things. So, but it has some nice, as I said, theoretical properties. So why do I care about star discrepancy? One of them is that there's a conjecture that's highly believed that these if you have deterministic sequences, the best you can achieve in terms of the star discrepancy is of order log n to the dimension divided by n, okay? Something like that. In 2 dimensions, it's been proved. On larger dimensions, it's believed to be true, okay? And they have actually found sequences like this. So basically, it says it shrinks to 0, right? As you increase this number of points, the star discrepancy will shrink to 0. It will cover the whole thing, yeah. Mm-hmm. Yes, exactly. Exactly. So I want to look at how good I'm how uniform I am. Exactly. This is a decay, exactly. Mm-hmm. This is how, it's shrinking to 0 as n increases, right? Because I'm going to fill in all the spots. So a random sample probabilistically will, the star discrepancy will shrink to 0 with probability 1, right? But this is a deterministic sequence. It still has something like this. All right. So they actually this some of these nets, digital nets, can be shown to have this property. They achieve this bound. And these are called low discrepancy sequences, and you want to use them, okay? Because the idea is you fill it better than a random uniform with the total n observations. All right. So another nice thing is this Cox-Mahlavka inequality. This gives a bound on the error. Any questions or comments? Feel free. All right. So this inequality will give a bound on my sort of estimation error, right? So remember, our notation, this is the expected, this is basically expected value of that guy, all right? I call that small g of x. So that's the objective function value at a given x. So no optimization again, right? So, and I look at my quasi-Monte Carlo estimate. So it's pretty much the same thing. So 1 over n, I just take a sample mean, except that these points are not random. They're just my quasi-Monte Carlo sequence. But that's the estimator. And if I look at sort of the deviation of this, the error of my estimate from what I'm trying to estimate, it's bounded by star discrepancy multiplied by, you can think of it as the total variation of my function g, okay? So what does it mean? It says basically, look, this tells me how good my sequence is, okay? If my sequence has a smaller star discrepancy, it fills the space better, so my error will be lower. Okay, makes sense. And the second part is, this is looking at some kind of a total variation of, so basically it's telling me how easy it is to integrate that function. So if this function is, not easily integrable, or, I cannot calculate expectation of this easily, obviously I'm going to get a much worse bound, right? So I cannot bound it that easily. So one thing is some functions actually have this infinite, but let's assume it's finite. And if we use a low discrepancy sequence, then, so quasi-Monte Carlo, this error will shrink to 0, right, of the same order as the star discrepancy. Okay? So if I use a low discrepancy sequence, I'll get this kind of an error bound. Asymptotically, this is better than the standard Monte Carlo error bound. This is for the standard deviation. It's going to shrink with 1 over square root of n. Variance is 1 over n, right? So if you look at these asymptotically, this is better. But if you look at them for some finite sample sizes, this dimension has to be really small. Even if it's a little bit bigger, you need a lot of sample size. But, this is an inequality. So it's not necessarily like it's a bound on how much the error is. So people have observed it's actually much better than what the bound gives us, or better than this quantity at least. Okay? So some observations. Monte Carlo error bound is free of dimension, which is one of the nice things about Monte Carlo, right? Why people use it a lot. You don't have to care about dimension. You can apply it. Of course, you're going to have some kind of a, you can do better than this, at least asymptotically. Again, as I said, n is large, d dimension is small, QMZ is better. So one thing is that for large dimensions, it can backfire as well. Okay, if you have small sample size. I mean, I have used some randomized Monte Carlo. So I'm going to talk about randomization in a little bit. But for small problems, it worked so well. For large-scale problems, it actually made things much worse. And it could be that I'm not using a good sequence and all of that, and it's also problem-dependent. So for some problems, they're looking at financial applications where this is like 100 assets, say. But then quasi-Monte Carlo works really, really well. So this is, for some problems, there's something called an effective dimension. So even though you have hundreds of assets, they might be correlated with each other. So the effective dimension is, say, 3 or 4. So it actually performs much, much better than, like regular Monte Carlo. So it's a little bit, dependent. Another thing is, obviously, this G is smooth, the integrants are smooth. It's supposed to work better. Again, it's with this total variation stuff. So, like, for example, Tito and one of his former students, they worked on this effective dimension for stochastic linear programs with recourse. So they try to identify which ones are important, employ randomized quasi-Monte Carlo, and then use Latin Hypercube or standard Monte Carlo on the other dimensions. It's easier to implement, and then it can work better. Okay, so there are some, if you want to learn more about those, this is something to consider. So, continuing on, this inequality, Cox-Mahlavka inequality, is difficult to compute. It's also a bound. So normally, how do we know the error bounds? Okay? So Monte Carlo, you can write statistical estimators, confidence intervals, and whatnot, right? You can use statistical theory. For this one, we just have this bound, which says star discrepancy. Can you calculate it? Yeah, it's not that easy. Total variation, sometimes yes, it's difficult as well. So this is where we get to the randomized quasi-Monte Carlo, okay? So include some randomness to estimate the errors. I'm going to talk about it a little bit. So first of all, how do we include randomness to this, sequence? Second, once we include randomness, how do we estimate our error of, this versus its expectation, right, that we're trying to estimate? So when we do the randomization, by the way, there are, again, many, many ways to do this. It's still an open area of research. The randomization also depends on the type of quasi-Monte Carlo sequence that you're using. Here's two things we want. We want each point to follow a uniform distribution over the unit cube. Okay, so I'm assuming Xi are, by the way, uniform. So if you want to do the inverse transform, that's fine. But for this, right, if I can do this, then I want that because the resulting estimator is unbiased. I always want unbiased estimators. That's always good. And then I want to preserve the low discrepancy because otherwise I'll use regular Monte Carlo, right? Why do I do the QMC and then randomize it and get that? So it has to be better than the regular standard Monte Carlo. Yeah, so that we want better estimators. So if you can have these two properties, go ahead, use randomized quasi-Monte Carlo. As I said, there are many different ways. I'm not going to get into details of this. As I said, it can depend on your type of QMC. So one famous and easy, very easy one, usually used for lattice rules, is that this is called Cranley Patterson random shift. So random shift is super easy. So you take your quasi-Monte Carlo point, the jth point, you generate a uniform, you add to that, and modulo 1. And that's your randomized point. Very simple if you want to write a code. Get your quasi-Monte Carlo from some available code, right? You can implement it when you're solving stochastic optimization problems. And here's how it works. It's, just a simple, so this is one sequence. As you can see, it's very like this, trying to fill the space like that. And you create this U, right? It will go like this. So somehow, if you go beyond the 1, right, on that dimension, you take mod 1, you take it down there. Same thing if you go on that dimension higher, you just take it back to do the mod 1, and so on and so forth. So you start with this, and then you end up with that. Still, filling the space, but a little bit more randomness induced here and there. Okay? So that's how it works. A simple way of doing it. Now, once we do this randomization, again, how do I get the errors? So this is a typical way when I don't know what the distribution or something, like I can create M of them, a number of them, right? Let's call them this randomized sequences with N sample points. Then for each one, right, I create my estimator. And then I take all of these and take an average of them. Then that's my actual randomized randomized quasi-Monte Carlo estimator. Okay, so I create M of them and take average overall, which is basically the average of all N times M points. All right. Once I do that, I can also see easily this is unbiased, and the error term can be estimated through M replications. I take a regular standard, sample variance calculation. This looks familiar, right? So I have M estimators. 1 to M. This is the mean of them. Take each one, subtract the mean or sample mean, square it, divide by 1 over the number of points I have, minus 1. That's the regular. So this will give me, I can construct confidence intervals and whatnot and do like a regular Monte Carlo. That's how you estimate the errors. Okay? All right. Any questions on this stuff? So again, I'm not giving you, there's many ways on each one of them. You can maybe, if you're interested, go to other resources. Next up, important sampling. How are we doing in time? When is the class supposed to end? When is the end time? 3. Okay. All right. So, important sampling. I want to basically get the sampling to the important regions that I want. All right, this is a little bit different than the other ones that we have talked about so far. So usually more useful, right? People use it for, people use it for these rare events. So in optimization, right, CVAR, again, Tito must have talked about this value at risk, conditional value at risk, right? Very commonly used risk measures. So you can think of this as roughly as the conditional expectation of what's happening in your sort of tail region here. So if it's like 95%, you look at the 5% tail, right? And you look at the conditional expectation. This one is the quantile, or actually the left quantile to be more precise. It's called the value at risk, and so on and so forth, right? So as you can see, if I take this alpha to over here, actually CVAR will give me an expectation. If I take this alpha all the way over there, it will give me, say, the worst case, like the worst that can happen. And I can adjust that and be more risk-averse and less risk-averse and so on and so forth. So it actually fits into the framework that we discussed. It's an optimization problem. You can write it like that. But the story here is if I look more and more into the tail, okay, I generate regular Monte Carlo sample. So if I generate 100 of these points, only 5 of them on average, right, will have a positive term here. So you're not using many of the samples that you generated to calculate, to get a good approximation of that. So what you want to do is you want to shift your probability distribution instead of something like this, or density, right? You want to have a lot more points here. That's how the importance sampling works. Right? Make sense? All right. So how does it work? Suppose it has density. So it could have probability mass function, or it could be more general. You can use Radon derivative. But let's say, just for simplicity, density. It works in other cases too. So my expectation, I write it as this integral, right, over the capital C here. And then, instead of using this density of the C, as I said, I want to maybe use another density that puts a lot more mass, or likelihood, over the region that I want to estimate. So now, that density should be absolutely continuous with respect to F. So some way of thinking about it is, so if there's any set that F is 0, right, then Q should be 0 as well. And if you have 0 over 0, we're going to deal with that. Well, I'm going to just talk about it now. So what we're going to do is we write the same expectation with a little bit of difference. So instead of F, I replace it by, I'm taking this integral with respect to this density Q, but then to get the same thing, I have to multiply it by something called, obviously, if you know this, likelihood function, right? So the likelihood ratio is going to give me F divided by Q for all C's again. So if both are 0, you set L to be 0, for example. Okay? So this way, what you're going to do is instead of sampling from this distribution, you're going to sample from that distribution and immediately use the likelihood ratio to get your unbiased estimator. Okay? So standard Monte Carlo, IID sample from the density F. Right? That's the main difference. Important sampling, I've changed my distribution. I'm actually sampling from the Q. Okay? So as I said, if I just put like another distribution that has a lot more over there, then I'm going to generate a lot more samples in the region that I want. Okay? So I sample from Q, but to get an estimate of this G of X, I have to adjust it with the likelihood. Okay? So I generate my samples from Q, and then my estimator is now defined like this. Okay? Any questions? All right. So again, you can see this is an unbiased estimator, and that's also easy to see, because if you plug in this likelihood, it's like F divided by Q. You generate the samples from Q, so you take expectation with respect to Q. Q goes away. All right, so you can take the integral and so on and so forth. You end up with the F again. So then it's an unbiased estimator. Okay, so you haven't changed the unbiasedness property, which is super nice. Yet on the other hand, you want to actually reduce the variance. But to do that, we need to pick this Q in a little bit more intelligent way. All right, so it depends on how I pick the Q. Let's see. So first of all, because of this likelihood, it's just F over Q. You can actually see, and I create the samples from the Q. You can see that, if I take expected of that, by the way, this was in the previous slide, right? It's an unbiased estimator. That's what it says. So I've got an unbiased estimator. Now, I'm going to look at the second moment of this. So why am I looking at the second moment and the first moment? Because I want to look at the variance, right? Variance is equal to second moment minus the first moment squared. So I want to look at this subtracted from that squared. And when I look at that, so this is samples with respect to Q. This is our regular old F, my regular density my nominal density that I started with. So I'm going to have that, this property. So when I write the variance of the importance sampling estimator, this is what I get. This squared, and this is equal to that. All right? Which means what? What is the variance of the Monte Carlo estimator? It's written there, but there's another way of writing it. What is the variance of g of xc, as I just said, right? It's the expected value of the squared minus expected value of g of x, right, squared, okay? So this term and that one is the same, but the first terms are a little bit different. So this one has this likelihood. So it has something to do with this Q, all right? So I'm going to reduce my variance if this thing is less than what's over here, okay? So this is the Monte Carlo variance. This is the important sampling variance, but the important term is this one. If I can somehow create a Q that will guarantee this, I will reduce it. Again, important sampling can actually backfire. You can create a Q. It's not that easy to come up with this thing. It's actually, again, an open area of research. There are many different ways of doing it, especially in optimization. It can get super tricky. But if you create in such a way that you just have this greater than or equal to, whoa, you actually did something you didn't want to do, okay? And people, observe this type of behavior. So, but the good news is, okay, so let's assume it's non-negative. If not, you can do the absolute values. So if I look at here, can I have a zero variance? Maybe. Zero variance means this whole term should be equal to 0, because n is fixed, right? So if I set this term equal to 0, actually I can get, whoa. If I can create this density, right, Q star, this is the optimal and zero variance density. If I create it like this, then I'm guaranteed to have a zero variability estimator. Absolutely great. But it's too good to be true, right? Can we create this? By the way, can you see that this will give a zero variance estimator here? Yes, no, maybe. Go back, back. So, I want, right? Expected g squared, what do I have? xc, L of c, something like this. So if I want to write this, I can say g squared xc, L is f of c, qc. If I take something like that, right? So if I end up maybe putting here q, I want something like this. F of c, right? So I want to get rid of one of this f of c. And what else do we have? We want to have an expectation, because in the end, I want to have the expectation of g squared, okay, ending up remaining there. So g divided by expected value of g of c, xc. Okay, so it should cancel out if I haven't done something wrong. Right, so this goes away, that goes away. This 2 goes away with this one, I think. Right, did I do this correctly? I think I might have made a mistake here. Oh yeah, expected will go up. So in the end, I'm going to come with, basically, I'm going to get the same thing. All right, so that's it. But it will actually give me zero variance. Perfect. It's unbiased. I will always obtain true expected value. No variability. Always get the expected value. But obviously too good to be true. Can you see why? Yes? Yeah. You have to know what this is. So you're trying to estimate this, and you're dividing it by the thing you're trying to estimate. It requires a knowledge of an unknown quantity, so you cannot do this, right? But it basically gives an idea of what you should do. So it should be proportional to this thing, which is saying what? Look, I'm interested in, say, some values that are larger, right? So basically, if I'm looking at the probability of being larger than a certain thing, I can set this to be an indicator function. Expectation of the indicator will give me the probability. So when I'm trying to estimate rare event probabilities, right? So when this takes value 1, so when it's larger, I should give a higher density over there, right? That's what it's saying. When it's 0, so I'm below that thing, I want to turn it off, then this should be also 0 or very low. So it gives you an indication it should be proportional to this, depending on the function and the F density as well. All right? So, but you don't know the proportionality constant, but you can still generate something like this. So this is used a lot to come up with some important sampling distribution. All right. Oh, I already told you. If you cannot, even when you try to do these things, sometimes it's difficult. The G can be very difficult and so on and so forth. It can backfire. I've already told you this. And one other thing you want, you can generate some kind of a complicated distribution, but you should be able to easily sample from that. So if you generate something that's super hard to sample from, why not use the F and maybe generate more samples, right? So it should be computationally easy as well. As I said, so exponential tilting will assume exponential family of distribution, and we'll try to find the parameters of that. You can use large deviations, non-parametric methods. Usually there's some exploitation of the problem structure, especially in optimization, because if you know something about your problem, you might want to focus your sampling effort there. As I said, still research going on in there, both in statistics, simulation, as well as stochastic optimization, right? So one thing people have tried, they say, I want the same family of distribution, like F and Q should be similar, different parameters. That's an easy way to do. And then even you write the minimized variance, so you use maybe stochastic approximation or some other method like stochastic optimization method to find the optimal parameter values. I mean, people have done a lot of things. All right. So here is recent examples, okay? I'm only going to give you a gist of this so that you see what's happening. This is a multi-stage stochastic program, for those of you familiar with this. It's a nested optimization problem, multiple stages, and it has that CVAR along with mean. But it's actually much worse than one stage because you have this nested CVAR. So you estimate at the lowest level, you make an error, right? And you go up, you put it into the second level. So you already have errors here, and then you do another error here. It compounds. Okay, so your estimation of upper bound, let's say, or this expected value, or the CVAR, gets really messed up. Okay, so if you can concentrate your sampling to the end, the tails, you can possibly do better. All right. So it's multi-stage, and there are more things going on, and I'm just giving you, as I said, I turned it into a two-stage and just giving you the basic idea here. So suppose I have a finite support, so let's say 100 realizations, okay? Usually, even if it's continuous, if you want to numerically solve a stochastic program or stochastic optimization, you have to discretize it by Monte Carlo or some other ways, right? So you can say it's got a finite number of realizations, and suppose each one of them has it's a uniform, discrete, so 1 over 100 probability mass on it, okay? And you want to look at the tail probability. And usually, you're going to sample, right? And you're going to estimate, do these function evaluations. These include, by the way, this whole bunch of nested optimizations. They're difficult to estimate. So you don't want to do that before, you sample, you look at this, and then you come up with your sampling distribution or density Q. That doesn't make any sense because you're going to do a lot more work. So they come up with, if you have a good approximation function, all right? So estimates the value cheaply. There's maybe some error. But the nice thing is, if it can order the values in the same way, more or less, especially in the CVAR, you order them and you look at the tail, right? Conditional expectation over there. So if we can order them in the same way and calculate it cheaply, so you give me a upper level, higher, first stage decision, for example, and the realization of this vector, and you estimate these things. And the idea here is you order them, and you get value at risk at whatever, say 95%. We all know what this is, right? I've just shown you the picture. It's the quantile, 95% left quantile. And you're looking at values about. So let's call this V of H of the approximation. You can do that cheaply. If you can do that cheaply, then here's what your importance sampling probability mass function is. If you estimate to be greater than the value at risk, so these are the regions that you want to sample from more, okay? Then you give this probability mass instead of 1 over, say, 100, like this is 100. If, on the other hand, you are on the other side, the undesirable side, so you're less than the value at risk, this is the probability mass function that you give, okay? So can you see what's happening? It's not that difficult, but just to sort of make it more concrete. So what did I say? So I have 100 realizations, let's say. So this is a probability mass is going to be 1 over 100, right? And suppose alpha is 0.05. So I'm looking at the 5% tail probabilities. And I have, let's say, these 100 values, right? Something like this. So, okay, so this is the last 5. Okay, so my original distribution is what? My original distribution gives each one an equal mass. So this is 1 over 100. That's my original uniform probability distribution function. But I'm more interested in calculating the conditional expectation over here. So let's take a look at what this guy does, right? So if I'm about, and this is how I estimate value at risk to be at that value, okay? So if I'm above that, I'm going to give what probability mass? 1 over 2 times, and by the way, this 1 over 2 is a little bit arbitrary, they say. You can also adjust it maybe according to how what's mean versus C-var that you're doing. But so 1 over 0.05 times this, right? What do I get? So 1 over 10, it's just like increased by like 10-fold, right? So basically put the mass, let's say, it's going to be actually quite higher, but let's say here for these 5 points. And then for the remaining part, what it is doing, it's doing 1 over 2. Now I have 100 minus the 5, so 95, okay? Something like 0.05, maybe somewhere here. So much lower on this side. So this is my original sampling distribution. Now what it has done, a lot more on this side, a lot less on this side, okay? So that's how you're going to do sort of importance sampling. And so they apply it to a financial problem. The financial problem, this approximation function, they use the current prices and the current asset allocation to come up with what the returns are going to be estimated. And it seems to work pretty well, especially if there's no transaction cost, because that estimation is much better. Okay? So again, the whole, oh, this should be Q, by the way. I'm sorry, there's a typo there. So finding this importance sampling is important. And the other thing you should know, it depends on X, typically. So you fix the X. What I mean depending on X is, right? So here you fix the X, and you have to come up with a value at risk for that X. You change your X, these cost functions will change. Maybe the value at risk is going to move. The ordering will change, and so on and so forth. So every iteration in an algorithm, you're trying to estimate these expectations. You have to come up with another sampling distribution, okay? Is this a typical thing in when you apply importance sampling to optimization? In statistics or simulation, typically classical, there's no optimization going on, so you create only one distribution and you're done, okay? All right, so, and this is, again, a Tito's paper, recent paper, another one. They first show consistency, optimal values converge and stuff like that. This is a chance constraint problem, not the ones I'm considering mostly. But they also come up with an important sampling distribution that not works for one given solution, but for a region, okay? Which is much better. They discard some of the non-optimal solutions. They know it's not going to be optimal over there. And they look at like a region, and they create an important sampling distribution that works for the whole region, not for each given x. Okay, and then they do some other things and can get significantly better results, but then sometimes it turns into mixed integer programs with a chance constraint, so it can be difficult to solve. All right? All right. Oh, they also create this L of x instead of L. So not only on the F and the Q, they also have some dependence on the x even more. All right. So just some ideas from the recent literature I'm giving you, all right? As I said, people try to do this for expectation in stochastic optimization, not really worth it. But for risk-averse problems, worth it. Control variates. Do you know control variates? Anybody? Nope? So this is least known of all of them. Yes, finally. All right. Oh, I got, maybe it will go into the next lecture a little bit. So control variates, our good old friend. I want correlations. I'm going to have correlations. It's going to work much better. Okay? So this time, unlike the antithetic variates, I don't care if it's negative correlation. So that one needed negative. This one would work positive or negatively correlated. You just have a negative term in there, so it will adjust accordingly. Okay? So either type of correlation will work. So it comes, so control variate, it has a control variable. So I've denoted C for simple, but usually, again, it will depend on X, just like the importance sampling. Depend on X, and we'll change with the C. So this is typically something you know easily. So if you're designing algorithms, if you can get this, during your algorithm, you can do, you don't have to compute it, you don't have to do additional work. It might save you time. Another thing is you should know something about it, so its expectation should be 0. This is, by the way, with respect to C. Typically, you know what this is, so you can you can subtract its mean, and then it will have mean 0. And you want it correlated with the, with this function. Again, positively or negatively is fine. All right. So there's another thing here. You take a scalar, lambda, and here's what you do. This is your original, this part is your original Monte Carlo standard estimator. You generate n points, IID, and you average them. That's it. When you use control variates, here's what you do. You add a scalar times your control. So this is, as I said, is going to depend on the C each time. You add your control to this. As you can see, when you add things, if you have correlations, the variance might go down, right? Just like we've seen in the antithetic one. Here, you're not adding like a GC of the antithetic variate, you're adding some control instead, okay? Now, because, by the way, you select it so that its expectation is 0, you take overall expectation here, this doesn't matter on average, okay? So you still come up with an unbiased estimator, so that's easy to see. Second thing is it will have this variance. So if you plug it all in, it's 1 over n sigma squared. The sigma squared is this variance. It's the thing we keep coming back. All right? So obviously this part, the first part, is the regular Monte Carlo, standard Monte Carlo variance. And then I'm going to have this term coming up. So lambda squared variance of the control, and then 2 lambda covariance. Okay? Now, suppose I want to minimize this variance. Okay? So setting lambda equals 0 obviously will give me the regular Monte Carlo, but that's not what I want. So how do I minimize this variance? This is a scalar. Suppose you know these quantities, so you just, it's a convex right? Univariate convex optimization problem. Take the derivative 2 times lambda variance plus 2 times covariance equals to 0. Set it equal to 0. When you do that, what do you get? lambda times variance equals negative of the covariance. So basically, you get this optimal lambda value. Okay? Once again, typically, you know your control, you know its mean, you can know its variance. It might be easier to deal with. That's what you want to select. The problem is you don't know G very well. That's what you're trying to estimate. So which means you typically don't know the covariance term fully. All right? So you can estimate it. And that's how people do it most of the time, because you don't know the exact quantity here. When you do that, by the way, before we do that, I think, let's plug this back in here. Okay? I plug that back in here. Here's what I get with the optimal lambda star. So this is, again, Monte Carlo variance minus I have positive terms here, so I'm guaranteed to reduce variance. Obviously, if there's covariance is positive, right? Covariance squared is positive. If there's some kind of correlation between them, I reduce my variability. Okay, so it's simple as that. All right, it's 3 o'clock. Let's see what we can do. Let me finish this part. So even though this may be known, the covariance unknown, I've already told that. So the problem is this. If I estimate this covariance term and use that as my scalar, it's no longer a scalar, right? It's a statistical estimator, essentially. It has its own statistical properties. It makes my overall estimator unbiased, okay? But in the limit, and people have used it, and it actually can still give significant variance reduction, despite that it gives you unbiased biased estimators. And also, as you go, take the infinity and scale it, right? It goes to this, essentially the lambda star, the best variance that you can get, something like that, all right? So it has this nice central limit theorem. So it can, for a large sample size, it can work, okay, even if you estimate it. But be aware, you no longer have unbiased estimators. All right, so using optimization, again, I've also used it myself, only seen it for fixed x to estimate the expectation, or subgradients, Hessians, and things like that. So this is during an algorithm, for instance. So this is some work that I've done. So for two-stage stochastic programs, not necessarily linear, it can be stochastic convex program. This can also have integer restrictions. Not the second stage, though. And I need stochasticity on the right-hand side, and this terms to be affine in Xi. Okay? So this will give me convexity on Xi, not X. I want my function to be convex in Xi. I'm going to exploit the convexity. Again, assuming independent components of Xi as we have done so far. Several classes of problems belong to this. So this is my Q function, the second stage optimal value. I'm trying to estimate its expectation. I know it's a convex function on Xi, not X, all right? My control variate is basically the Taylor series approximation, all right? At the expected value, I take a Taylor series approximation. It's a good approximation around the Xi values, but as you go further away, it's not as good a control, okay? So in our algorithm, we've actually also have partitioning in that algorithm. So what we do is we partition the support of Xi. So in this case, it's one-dimensional, right? So if I have a convex function, expectation here, I take this. Now I partition it into two, this part and that part. And here I look at the conditional expectations. Now I use two controls for each partition. Once I do that, this obviously is much better on this side, and this is much better on that side. And if I increase my partitions and use a bunch of these control variates, right, they're actually following very closely the convex function, especially in regions where it's flatter. So it starts, let's say, with 20 times variance reduction, and it goes to 1,000 times variance reduction as you partition, right? I mean, because it's it's finding all these, it's piecewise linear, it's finding almost like creating the convex thing on its own. But it's restricted because it's only for a fixed x. So every iteration, you only estimate the objective function values. You're not like optimizing it. Okay, so I'm not aware of control variates and optimization, like also taking the minimization. All right, I'm going to end it here. And then next lecture, I have some more coming up on this, and then we'll continue. All right, thank you.